And SN2 reactions display a rate when the rate here is equal to the rate constant K times the concentration of an alkyl halide that's being reacted and the concentration here of whatever the nucleophile is. So the rate is linearly dependent on the concentrations of the two species. And the brackets like this indicate concentrations. So we are dependent on the concentrations of both. And so remember that in this that K here is, this is your rate constant. Another hallmark of the SN2 reaction is that once you undergo the reaction, you end up getting inversion of configuration. So if you had R, you would, after the reaction, end up with S. So we show this, what we call up here, gives us second order kinetics. Because it's dependent on both. And then we also end up getting inversion of our configuration. So if you have R, you go to S. If you had S, you would go to R at the end of the reaction. Now, the other aspect of SN2 reactions is that it is a concerted reaction, meaning that once the nucleophile comes in, it's going to come in and we're going to end up getting bond breaking and bond forming at the same time. So that means that the leaving group will also begin to leave. So what you can see is, in an example would be where you have some nucleophile. So I'm just going to write NU with a minus charge on it. And we have some alkyl halide. So let's do CBr. And let's fill this in here. So and so what's going to happen, as you can see, that as this begins to go in and attack this carbon, and this is also going to begin to leave, we're shown with a transition state that looks something like this. And basically what we have at this point is the nucleophile coming in and the leaving group leaving. Notice the other point here that this nucleophile is coming in behind the leaving group, so it comes from the back side of the leaving group. So we have attack behind the leaving group. And so now I'm just going to kind of draw this little arrow over here, and we end up in this case with now our nucleophile attached to now our carbon, and we end up with our inversion of configuration that we see. And this gives us our product. The substrate preference in SN2 reactions, and so in general SN2 reactions need unhindered substrates. So substrates in SN2 reactions. So what we need here are, as far as the rate, we can think of that a bulky substrate basically blocks the nucleophile, right? So it's going to prevent the nucleophile from coming in. So we can just say that this prevents the nucleophile approach. And so what we need is something that is, we can think of it as primary is better than secondary, which is better or greater than tertiary. So these two are really the only ones here that will react with in an SN2 reaction. This tertiary does not react. Now, with that being said, we also have to consider the fact that things that are what we call vanillic and aryl halides. So vanillic, remember, vanillic is attached to a double bond. Vanillic and aryl halides don't react with SN2 reactions. So something that looks like this, and something that looks like this, no SN2. Okay, so those are your substrate limitations for SN2 reactions. And so the best thing is we also want to have something that is a good leaving group. So when we speak of halides, we can also consider the fact that we have, as far as the leaving group, needs to be decent, and we'll talk about the leaving group later, but these can be considered as halides. I right there. And tosylates. Halides and tosylates there for leaving groups. Okay, now we need to talk about the nucleophile in the SN2 reaction. So the nucleophile, and now this can be any species that has either, it can be neutral or negative, let's just say that. Neutral or negative. And the other thing is that if neutral, you need lone pairs. Okay, so if it's neutral, you need lone pairs, and how strong this nucleophile is depends on a couple of things. The strength depends on 1, the substrate, depends on also the solvent, and it depends on the reactant concentrations. So let's just say reactant concentrations, which I'll abbreviate with this little bracket. Okay, so this is what the strength of the nucleophile depends on, these three things, right? And so, of course, obviously, if it has a negative charge, it's going to be much stronger than something that has no negative charge, typically in general. Just as an example of some common nucleophiles that you might see, so starting from less reactive to most reactive, water is less reactive than something like an acetate, which this is an acetate. Even though this is negatively charged, if you come over here, the acetate, of course, isn't as strong because it does have the ability to resonantly stabilize the negative charge. So here is this resonance structure of this acetate. You, of course, can move these electrons down and kick these up over to here, and so you end up with the resonance structure of acetate. And then the next nucleophile, as far as strength, would be something else that's neutral. So something like an ammonia. And then moving from there, we can see we get into some of our halides. So Cl minus, and then another good nucleophile, but not really one of the best, is OH minus. And the deal is that nitrogen by itself is more basic than oxygen, and this OH minus is more of a base than it is really a nucleophile. So it would rather act in a base as a base other than as a nucleophile. Then we get into something like CH3 minus. We're getting into now more stronger nucleophiles. And finally, I minus is a decent nucleophile. And then something like the cyanide anion, which is a nice strong nucleophile. So these are just some common nucleophiles that you might see, and you can tell in general the ones that don't have a charge are less reactive, except for this acetate group that's right there, and that's because of resonance. So we can just say resonance of an acetate. Right, and this is what causes the nucleophilicity to kind of go down as far as that on the acetate So the trends in this, you can see that nucleophilicity roughly parallels basicity. So if it's a strong base, it's likely to be also a strong nucleophile. And nucleophiles get stronger as you go down a column of the periodic table. So um, we increase as you go down a column on the periodic table. So for instance, I minus is greater than Br minus, although not by a whole terrible lot, but it is. So I minus is greater than Br minus, which is also greater than Cl minus. Right, so we are going down the periodic table as we go towards iodide. And normally, of course, negatively charged nucleophiles are stronger, acetate notwithstanding. So this then gives you some idea about some nucleophiles for SN2 reactions. So in general, for an SN2 reaction, you want a good, strong nucleophile to take place because we want this reaction to happen fairly easily. Groups in SN2 reactions. You typically want good leaving groups. So good leaving groups are things that can stabilize negative charge very well. So things that are large, so for instance, bromine, iodine, those things are good leaving groups. So just in general, things that are really poor leaving groups typically are something like that has a C minus. This is a very bad leaving group. Something that also has a negative charge on it, so something like an OH minus is a poor leaving group. Something like an N R2, where R can be either hydrogen or an alkyl group minus. This is a very poor leaving group. You typically don't see those. And then something actually like fluorine, F minus. This is a very bad leaving group. And then you're getting into the halogens, a little bit more of those. So Cl minus is okay. Not the best, but it's still okay. And then something like Br minus is pretty good. I minus is even better than that. And remember, what's funny about this is that this is both a good leaving group and a good nucleophile in an SN2 reaction. And then another good leaving group is a tosyl group. So tosyl looks like this. So this would be a tosyl group. So these are typically good leaving groups. So in general, for leaving groups, the better they are, that they can stabilize the negative charge, the better the leaving group they are. So these in general are basically what we would consider poor leaving groups. So basically they're not going to react well in SN2. Now, another way to think about this is that things that that are the weak bases of the stronger acids. So, for instance, the reason why Cl here is a good leaving group is because HCl is a strong acid. So, conjugate bases of strong acids are also what you can consider as good leaving groups. Okay, so the final component for SN2 reactions that we need to talk about are solvents. And so SN2 reactions have an importance on the solvent that you use. And so basically you want something that is aprotic. And so what does that mean? Well, that means something that doesn't have either a proton that it can use. So solvents like or that contain some OH or NH group on it are bad for SN2 reactions. So essentially, SN2 reactions won't work very well in that. And the reason is because these solvents like this tend to form a solvent cage around a nucleophile. So for instance, they do what is called solvation. And what this means is that you can have some nucleophile, we'll just write Nu minus, and if you have something that has an OH it kind of forms this cage around it like so. And what you can see is that on each of these, here we have a dipole, where that's a partial minus and this is a partial plus. And so what's going to happen is it's going to sort of chelate or solvate to your nucleophile in each case. And what this does is it reduces the nucleophilicity, so lowers the energy of the nucleophile. And so therefore it makes it less reactive, and these are not good for SN2 reactions. So anything that has something like this is bad for an SN2 reactions. So what do you want then for an SN2 reaction? So what you want for an SN2 reaction is what we call polar aprotic. Polar aprotic is what we want for an SN2 reaction. So what does that mean? Well, What that means is that they have a dipole, just like these guys. There is a dipole right here, as you can see where my cursor is. Yes, they have a dipole, but they don't have the hydrogen that can chelate. So we can say but no H. So we don't hydrogen bond to our nucleophile. So some examples of good solvents for this in sort of an order of reactivity. What you can see, for instance, if we had something like methanol, this of course has a proton here, right? So this will be polar A product, so this one will be considered bad for SN2. And then of course water is not the best also for an SN2 reaction, so bad as well. And then you get into something like DMSO. You get into something like DMF and acetonitrile. And then something called HMPA. These are actually good solvents for SN2 reactions, and so I'll throw in another one that is probably in this area right around here in between these. Another good one, I'll just put right here, is acetone. This is also a good solvent for this. So DMSO looks something like this, and this is dimethyl sulfoxide. DMF looks like this. So this is dimethyl and N-dimethyl formaldehyde. And acetonitrile, you can envision, looks like this, where there's also this strong dipole that goes in this direction. So we have partial plus, partial minus here. And then HMPA is hexamethyl phosphoramide, so it looks like this. And so that's this guy right there. So these are all examples of good solvents to use in an SN2